Here is a combined summary of the 4 pages. SiMWiSense is a novel framework for simultaneous multi-subject activity classification through Wi-Fi signals, addressing scalability and generalization challenges. Scalability is achieved by utilizing multiple Wi-Fi devices as channel state information (CSI) collectors, where the closest device to a subject is used for classification. Generalization is addressed through Feature Reusable Embedding Learning (FREL), a brand new few-shot learning algorithm. Wi-Fi sensing leverages tiny changes in CSI to detect physical changes in the environment. The framework proposes using multiple CSI collectors to capture independent propagation paths between the access point, AP, and devices. Experimental results show that the device closest to the subject dominantly characterizes the channel property, resulting in better classification accuracy. The SiMWiSense framework consists of 3 task blocks: sensing, preprocessing, and learning. The sensing block captures CSI data, the preprocessing block extracts features, and the learning block uses FREL to classify activities. FREL combines embedding learning and metalearning approaches, achieving better performance through fine-tuning with only a few additional samples. An extensive data collection campaign in 3 environments with 3 subjects performing 20 activities simultaneously demonstrates SiMWiSense's classification accuracy of up to 98%. FREL improves accuracy by 85% compared to traditional CNN and up to 30% compared to state-of-the-art few-shot embedding learning (FSEL), using only 15 seconds of additional data for each class. The decentralized sensing system, SiMWiSense, utilizes FREL to adapt to new scenarios with few data samples. The FREL model consists of an embedding network and a classifier, trained jointly during metalearning and fine-tuned on a small portion of data for better adaptation to new tasks. The cascaded learning block uses a 2-stage detection approach, reducing complexity and enhancing flexibility in a dynamic system. The paper introduces SiMWiSense, a novel Wi-Fi sensing system capable of detecting and classifying human activities in real time. This system operates in 2 stages: subject identification followed by activity classification. Utilizing a convolutional neural network, CNN, as the baseline model for both stages, the authors also propose a new feature reusable embedding learning (FREL) strategy to enhance the generalization capability of the model. In an experimental setup consisting of 3 environments: classroom, office, and kitchen, with 3 subjects performing 20 different activities, the authors trained 3 separate models for each monitor using data collected from each corresponding subject. They evaluate the simultaneous multi-subject activity classification performance of SiMWiSense with the baseline CNN and find that the average accuracy in the environments is high, ranging from 97.37% to 98.51%. The performance discrepancy of monitors M1, M2, and M3 is less than 2%. Achieving an average accuracy of 98.0%, 96.84%, and 98.54% respectively. The authors further study the trade-off of the subcarrier resolution and the SiMWiSense performance, observing that the system performs worse with lower subcarrier resolutions. However, they find that extensive feature extraction techniques or higher sampling frequency can compensate for this, albeit at the cost of increased computation burden. The paper demonstrates the effectiveness of the FREL strategy in enhancing the generalization capability of the model, especially when dealing with new tasks that the model has never seen before. The evaluation of SiMWiSense in 3 different environments shows that the system achieves an average accuracy of 98.66% with 242 subcarriers, but the accuracy decreases to 84.92% and 62.76% when the number of subcarriers is reduced to 80 and 20, respectively. The confusion matrices of the baseline CNN model reveal that the top 3 classes that are hardest to distinguish at lower subcarrier resolutions are wash hands, rotate, and brush. The performance of SiMWiSense with FREL is also evaluated, and the results show that FREL excels in generalizing to new environments and subjects. The overall performance of SiMWiSense with FREL in new untrained environments improves by 86.06%, 87.56%, and 86.90% when the embedding network is trained in classroom, office, and kitchen, respectively. FREL also surpasses FSEL, few-shot learning, by 25.71%, 17.43%, and 15.56% in the same environments. The confusion matrices of FREL and FSEL reveal that FREL achieves higher accuracy and is more robust in distinguishing activities. FREL can also generalize subject identification in new untrained environments, achieving an accuracy of up to 96.53%, whereas the traditional CNN limits to 6.19%. FREL demonstrates an accuracy boost of 17.79%, 17.93%, and 17.55% in classroom, office, and kitchen, respectively, compared to FSEL. Moreover, FREL can generalize the monitors across the environment, achieving an average accuracy of 91.71%, 94.51%, and 94.78% in generalizing the other monitors while trained with Monitor 1, Monitor 2, and Monitor 3, respectively. This enables any system to be trained only on one monitor and deployed with n number of monitors with only 15 new data samples from each monitor. The results demonstrate the robustness, reliability, and strong adaptive capability of FREL to new environments and subjects. The proposed FREL model can be used for simultaneous activity sensing and subject identification in various environments, with high accuracy and minimal training data. The proposed SiMWiSense framework is a groundbreaking approach to simultaneous multi-subject Wi-Fi sensing, leveraging channel state information (CSI) for device-free and location-independent human activity classification. It addresses the limitations of existing single-subject approaches, emphasizing the need for a more comprehensive and robust system. SiMWiSense employs the Fast Adaptation Reliability Evaluation Learning (FREL) algorithm, which adapts to changing data distributions and generalizes to new environments and subjects with minimal new data. Its performance is evaluated in 3 scenarios: classroom, office, and kitchen, involving 3 subjects performing 20 activities simultaneously. A comprehensive review of related work in Wi-Fi sensing is provided, discussing RSSI-based, PWR-BASED, and CSI-based methods, as well as deep learning applications in CSI-based Wi-Fi sensing, such as human activity classification, gesture recognition, health monitoring, and indoor localization. The FREL algorithm outperforms traditional CNN-based approaches and state-of-the-art few-shot learning models, achieving an accuracy of up to 98.94% and surpassing existing methods by 85% and 20%, respectively. A thorough analysis of the system's performance in different scenarios demonstrates its robustness and adaptability. The paper concludes by highlighting the significance of SiMWiSense in enabling device-free and location-independent human activity recognition, with potential applications in healthcare, smart homes, and surveillance. It also acknowledges the limitations of the approach and suggests directions for future research.